So 4.2 inference using normal and t-distributions. Okay, so first of all we have the syllabus, and then after that you see the notes here. Inference using normal and t-distribution. So they say if we take a sample size from a normal population of known variance, sigma square, then no matter what the sample size, the mean is a normal distribution. The mean is mu, the variance is sigma square over n. Okay, exactly. So that means they are trying to say our first concept here. The first concept is if x is normal distribution, then x bar will be normal distribution. For whatever n. For whatever n, the x bar is still normal. Okay, now let's continue. The second information. If you take a sample of size n greater than 30 from any population distribution, that means it can be binomial distribution, Poisson distributions, where sigma square is known, then by central limit theorem, x bar is a normal distribution also, with mean mu and variance sigma square over n. Okay, so they are trying to say something like this. If your x is whatever distribution, for example binomial distribution, for example Poisson distribution, then as long as n is greater than 30, then the x bar will be a normal distribution. So we can use central limit theorem to claim that it is a normal distribution. Okay, now next one. If you take a sample of size n greater than 30 from any population distribution with unknown variance, now we don't know the variance, just now we know variance, we know sigma square is known, now we don't know, then sigma square is estimated by calculating s square. So if you don't know the population variance, you have to count it out by using this formula. S square equal to 1 over n minus 1, sum of x square minus sum of x square over n, or you can use this formula, 1 over n minus 1, sum of x minus x bar square. So we use this formula to estimate the population variance. So once you estimate that, then you can also claim that it is a normal distribution. X bar is a normal distribution. Okay, so from here we know the third information. The third information is if x is any distribution like binomial, like Poisson distribution, and n is greater than 30, sigma square is unknown. So you have to count the unbiased estimator for the population variance. That means you have to count the s square, and then after that it will become normal again, mu s square over n. So you can see the difference between the second one and the third one is, this one we use the given variance, this one we have to count the variance, the population variance. Okay, so now next.
So as long as variance is given or n is more than 30, we use normal distribution. And if it's not, then you use t-distribution.
Yes, correct. So that is the thing. So that's why over here they are starting to lead us to the t-distribution. So they say if n is greater than 30, you use normal distribution. If n is less than 30 and you don't know the variance, then you use t-distribution. Okay, so that's the thing. Okay, so finally we come to a situation where when n is less than or equal to 30 and unknown variance, and then we use t distribution. Okay, so let's move on. Okay. On this page, we have the introduction to the t distributions. Okay, so let's see here. Suppose a sample of size n is drawn from a normal distributions, then the one sample t statistics, t equal to x bar minus mu over s over square root n. So this is the formula to count the t statistics. Okay, so when you look at this formula, right, you can see s there. You can see s here. So that means the thing is we don't know the population's variance. This one is unknown. So you don't know this, and you have to use s squared to estimate. You get the unbiased estimator for the population mean, the s square, and then you square root it, you get the s, and you put here. Then you get the test statistics. So has the t distribution with n minus 1 degree of freedom. Degree of freedom is denoted by v. So v equal to n minus 1. So when you use t distribution, you have to count the test statistic, you have to count the degree of freedom. Okay, now this one we just go through quickly, see what happened here. Comparing density curve of the standard normal distribution and t distribution. Standard normal distribution, right, is something like this. Z equal to x bar minus mu over sigma over square root n. So this is the standard normal distributions formula. So it looks kind of same, you know, it's just that we don't know the sigma for t distribution, but this one we know the sigma. Okay. Now the density curve of the t distribution is similar in shapes to the standard normal distribution. That means they're both having the bell-shaped curve or a mountain-shaped curve. The spread of the t distribution is a bit larger than that of the standard normal distribution. That means the standard deviation is greater. The t distribution has more probability in the tails and less in the center than does the standard normal distribution. So you should see the difference. The tail is expected to be higher, and then the center is expected to be shorter. So as the degree of freedom increase, the t distribution curve becomes even closer to the standard normal curve. So if this is big enough, then their curve looks the same. Okay, now let's see next one. The one sample t confidence interval. Let's see, one sample only. So you see the information here. The one sample t interval for a population mean is similar in both reasoning and computational details to the one sample z interval for a population mean. That means same concept. Choose a simple random sample of size n from a population having unknown mean mu, and confidence interval for the mean is this formula. This formula is for the confidence interval. So confidence interval, we use this formula where t is the critical value for t n minus 1 distribution. So they put n minus 1 there because of the degree of freedom. And then margin of error is t s over square root n. Okay, so confidence interval will look something like this. You have a t distribution graph, and then the mean is here. So we have a mean minus with something, t s over sub n. We also have mean plus something, t s over sub n. So what we can see is when you count confidence interval, we are counting an interval from this value to this value. Okay, so you see one example here. Suppose we need to construct a 95% confidence interval for the mean mu of a normal population based on a sample of size n equal to 12. What critical value t should be used? Okay, so first, to count the critical value t, right? Okay, so let's see the information here. We have n equal to 12. The degree of freedom is v equal to n minus 1. Degree of freedom is 12 minus 1, which is 11. Okay, so we get the degree of freedom, and then now they give 95% confidence interval. So you should expect something like this. 95%, 0.95 in the middle, 0.025 on both sides. So the t critical is here. This one is the negative t critical. Okay, so in order to find the t critical, so what we need to do is we have to look at the table. Okay, so let's see the table. First you have to refer to the MF19. Okay, so I put it here.
So how is the values for the graph created?
Yeah. What you say again?
How is the values for the graph created again?
You mean how we get the value from the graph? Oh, okay. We get it like this. You see the data booklet here. We turn to the t distribution, the table. Okay, this is the one. Critical values for the t distribution. And you see the graph has certain characteristic like this. They count from the critical value and all the way to the left. Okay, so when they come back to our situation, okay, so you should expect they count from the critical value and all the way to the back. So that means you should expect to take these two values to be your p. So your p is hence 0.975. Your v is 11. Okay, let's come back to the table. 0.975. So we look at this column, and 11 degree of freedom. So at the end we have to take this value, 2.201. Okay, that is the critical value. So the critical value is hence 2.201. So of course at the meantime you look at the graph and imagine. So 2.201 is the value on the right, and negative 2.201 should be the value on the left. So the critical value, we just take the positive value. Okay? But in terms of graph, they are positive as well as negative. Okay. Now let's move on. Hypothesis test when a small sample is drawn from a normal population of unknown variance. Okay, so again, it is t distribution because small sample and unknown variance. So you see the steps. We will be given values of x, which is the sample, and the mean value, which is a. Okay, so we set up the null hypothesis, mu equal to a. Okay, so alternative hypothesis, it depends on the question. It can be mu less than a, mu greater than a, or mu not equal to a. So it depends on how the question asks. So you have to read through the question and determine which one should you take. Okay, so if you take mu less than A and mu more than A, means one-tail test. One-tail test. So we call it one-tail test basically because of this. Imagine you have a graph. So when they say mu less than A, so basically that means less than A. So it's this situation. H1 region, this is the HO region. Okay, less than A. So if they take H1 mu greater than A, that means the graph looks like this. H1 is always a small region. So you have T critical here. Just now this one is negative T critical. Okay. Then the H1 is here. The HO is here. But if your H1 is mu that is not equal to A, then you should expect there are two-tail tests. So the two-tail that means is, of course, this tail and this tail. These two are known as one tail, so it's this tail and this tail. So these two, this is one tail test. Okay, so this is two tail. So again, we have the HO region. The side is the H1 region, and then the negative T critical and the positive T critical. Okay, so we have two tail and one tail. Okay, now mu not equal to A means a two-tail test, which is this one. Calculate sample mean from the data given. So you have to count this first, count the mean. Then you have to count the unbiased estimator. Use this formula again. Then you have to calculate the test statistic. Then you have to find out the T critical value by using the degree of freedom, V equal to n minus 1. Then you have to look for the confidence interval, and then after that you have to check the table, the same table like just now. So case 1, if H1 mu greater than A, mu greater than A, that means, okay, you look at the graph at the same time. Mu greater than A, it refer to this one, mu greater than A. Probability of T lesser than or equal to T critical is equal to 1 minus significant level. So they are trying to talk about this shaded region. Okay, so what are they trying to say is 1 minus significant level. So significant level is here, alpha. So this one is 1 minus alpha. So they are trying to say something like that. Now, the critical region is when T greater than T critical, which is here. That means in this situation, we will reject HO, H0, the null hypothesis. And then we have to take H1 then. Okay. So case 2, if you have H1 mu less than A, mu less than A, of course, it refers to the graph over here. This one. Now what they said is, probability for T less than or equal to T critical is equal to 1 minus significant level. Okay, so of course maybe when you look at this, you feel like this one is like slightly different. Okay, actually it's not actually. So if we put it in this way, if we take this graph, we swap, because they are symmetry, so we just swap. The negative T critical will shift here, T critical. Then this is alpha, this is 1 minus alpha. So after you swap, here is alpha, here is 1 minus alpha. So it seems like it's going back to the same situation like this. Alpha, then here 1 minus alpha. Okay, so then this thing makes sense again. So the probability of T less than or equal to T critical is 1 minus significant level. So that means it refers to this part. this part, less than or equal to t critical is 1 minus significant level. So the alpha is significant level, but originally it's like this. You swap, then you will see it makes sense. Okay, then critical region, when t less than negative t critical, that means here less than the negative t critical, so they enter this small region. This small region is where we reject HO and we take H1, so we call this critical region. Now let's move on. We have next page, case 3. Okay, case 3 is where mu is not equal to A. Mu is not equal to A. If you still remember just now, we have two-tail test. So where here is alpha over 2, here is also alpha over 2. We take the significant level, divide by 2, and give it to the two tails. So you want to find the t critical is here. The negative t critical is here. Okay, so you want to find pt less than or equal to t critical, you have to do 1 minus alpha over 2. 1 minus alpha over 2, and then you get this. So they're talking about this region. Okay, so you want to find that region, you take 1 minus alpha over 2. 1 minus this, and then you get this one. Okay, and then critical region is when the t smaller than negative t critical. That means here. When the t more than the t critical, which means here. So this is the critical region. It is a region where we reject HO. Okay, now let's move on. This statement must be written in this way. If t is greater than or less than the t critical, we reject HO. Now compare t with t critical and see whether it lies in the critical region. If it lies in the critical region, we reject HO. If it doesn't lie in the critical region, then we accept HO. Okay, so write the concluding statement. So the whole process is like that, kind of complicated. Now let's see example. A machine is producing circular discs whose radius is normally distributed. Their radius historically has been 5 cm. So when I say historically has been 5 cm, so this is actually the mu. The mu is always the previous information, or from the previous study, you get the mu, the population mean. Okay, now the factory foreman believe that the machine is now producing discs that are too small. Okay, this is important. This will help us to determine your H1 is taking mu less than 5. Too small. We take left hand side as the tail. Okay, so a sample of 9 discs is taken and their radii are these values. Okay, so we have n equal to 9. This is n. Carry out a hypothesis test at a significant 10% significant level. So that means they give alpha equal to 0.1, the 10%. Okay, so we set up the null hypothesis, mu equal to 5. Alternative hypothesis, mu less than 5. Significant level is 0.1. Degree of freedom is n minus 1, which is 9 minus 1, that is 8. Okay, then after that, we don't have populations variance, so we have to use the unbiased estimator. 1 over 8 minus 1 9 minus 1. Then we have to find out the square of the theta. So that means imagine you take 4.8 square plus 4.9 square plus 4.5 square and so on, add up all the square, and at the end you will get 214.43. Okay, then followed by mean square over n. Mean square over n. Okay, mean is not found yet. I find the mean here. Mean is you add up the theta. So imagine you add up all this 4.8, add up all the way to 5.0, then divide by 9. So you will get 43.9 over 9, 4.88. So you get the mean. Okay, so after that, because of that, now come back to the s square. Okay, so remember our s square formula is s square equal to 1 over n minus 1 sum of x square sum of x power 2 over n. So I'm using this formula. So because of that, I know sum of x is 43.9 square over 9.
So because I learned it like you multiply everything by n, so the outside becomes n over n minus 1, and then you divide everything inside the bracket by n.
Can also, yeah. So that means you are talking about the other form, right?
Yeah, n over minus 1 times variance.
Times variance.
Times my square, yes.
Okay. Yeah. So it works also. Sum of x square over n minus mean power 2.
Yeah.
So this one works as well. Okay, so it's up to you. Then at the end, you will get 0.03694. Okay, now after that, we have the s. We square root that value, 0.1922. We square root the 0.03694, then we get this. Okay, so now we can use the formula to count the test statistic. T equal to, okay, I write down the formula again first. The formula for the test statistic, x bar minus mu over s over square root n. So we use this formula. So we get 4.88 minus with 5 over 0.1922 over square root of 9. Square root of 9. Okay, then we count this. We get negative 1.873. Okay, so this is called the test statistics, and we have degree of freedom 8. Now let's use it to count the critical value. So imagine this is left tail and this is left tail, so it's something like this. Left tail here 0.1, here 0.9. This is the negative t critical. Okay, so when we check the table, so we just check in this way. Okay, let me put on the screen first. MF19. Okay, so what we need to do is we take, imagine you swap the table. Okay, so you swap the table, you swap this table, you swap until it look like the other way around. 0.9 here, 0.1 here. So you count this T critical instead. So the T critical based on the table 0.9, degree of freedom which is 8, you get this one 1.397. Okay, so this is 1.397, but our situation is negative value, negative 1.397. So T critical is negative 1.397. Okay, now our test statistics, this value is in the critical region. Negative 1.8 is here in this small little region. Okay, so now we just said it, our T is less than negative T critical, so it's in the critical region, so we reject HO. Okay, then we just make a conclusion saying that the factory Foreman belief is correct. Okay, so that's how we handle it. Okay, now let's move on. Next page. Testing for difference between means. Okay, now we have two means. Both are normal distributions. So you can see here, both of these are n, that means normally distributed. X and Y are either normal or approximately true if nx and ny are greater than 30 by central limit theorem. So that means normal at the end, because n is greater than 30. So provided x and y are independent, x bar minus y bar, the mean you minus, the variance you have to plus. Be careful with this, so we have to plus because of the square. Okay, the square will make the negative become positive, so that's why we plus. Okay, so standard deviation, you have to square root this. Test statistics, you can see the formula, x bar minus y bar minus mu x minus mu y divided by the standard deviations. Then after that, for hypothesis test, same method will be used as before. However, here we will use the normal distribution. So when you check table, you have to check the Z distribution and not the T distribution. Critical value would be found the same way, only T would be replaced by Z. Then we will compare test statistic with the critical value to get the results. If variances are unknowns, we will estimate them given that the sample size of both x and y are greater than 30. So that's the condition. Okay, so we use Z distribution if it is greater than 30, if n is greater than 30, although we don't know the variance. Okay, so if the variances are unknown for x and y, but both have a common variance, so this one very important, common variance, same, that means x and y have the same variance, and we are testing HO so that mu x minus mu y equal to C. A two sample T test is used. What are we trying to get from this statement is, when should we use T test? We use T test when we don't know the variance and the question said they have a common variance. We don't know the variance, but there is a common variance. Okay, so then we use t-test. X and P are normally distributed, and here SP square is the unbiased pool estimate of the common variance. So we have to estimate the variance by using a different formula. Compared to previous one, there is one formula, now we have another one. So SP squared equal to this or this. So you can use this formula to estimate the common variance here. So we need the common variance, and then the degree of freedom nx plus ny minus 2. Minus 2 this time. Okay, so let's move on first. A little bit more information. Okay, so now the test statistic is given by this formula. T equal to x bar minus y bar minus mu x minus mu y square root. So this is the common variant just now. Previously, if you still remember the formula, the sigma square x and the sigma square y are here. Now they have the same variance, so they can factorize it. Factorize and put in front. Yeah. So let's see example. A scientist wishes to test whether new heart medications reduces blood pressure. Okay, reduces blood pressure. Important. H1. Something less than something. Okay, less than. 10 patients with high blood pressure were given the medication, and their summary data is these values. Okay, so we have this value with high blood pressure. 8 patients with high blood pressure were given a placebo. Placebo means a fake one. Okay, a fake medicine. You eat something that is not helpful in treating the high blood pressure. You just eat something that you don't know what is that, but psychologically you feel like you're eating medicines, but in fact it is not the real medicines. So, and their summary data is this and this. Carry out a hypothesis test at 10% significant level to see if the medication is working. Okay, so if the medication is working, right, we should expect the mu x to be lesser than the mu y if it's working. It is not working, right? Then we should expect the mu x and the mu y are same only. You eat the medicines or you eat the placebo, you get the same blood pressure at the end. Okay, so because of that, we set up our HO. If you don't want this, you just put mu x equal to mu y. No difference between the new discovered medicines and the placebo. Same. But if it works, if the medication works, the new heart medication works, so you should expect mu x to be smaller because it will make the blood pressure smaller. So mu x supposed to be less than mu y then, if it works. So if not, you just bring it to the side like this. So we have two options. Significant level 0.1. Let's count the mean first. The mean of x. 1271 over 10. The mean of y. 1036 over 8. Okay, now we count the common variance. Okay, so the common variance, we use the formula. So the formula that we are going to use is, let's see, we have two options there. So I use the one which is sum of x minus x bar square plus sum of y minus y bar square over nx plus ny minus 2. Okay, then I just substitute the value 640.9 plus 222, 10 plus 8 minus 2, then end up with 53.93125. Okay, then I square root, I get 7.344. Now I count the test statistics. The formula is written on top, this formula. Okay, so I just substitute 127.1 minus 129.5 minus mu x minus mu y. We take the HO one, which is 0. 0 come from here. Okay, so over square root the SP square. SP square is the 53.93125. Then 1 over nx, 1 over ny. Okay, then we count this, we get negative 0.688. Okay, then degree of freedom, nx plus ny minus 2. So we just take 10 plus 8. 10 plus 8 minus 2, we get 16. Okay, so we have to check the table. To get the T critical. Okay, so our significant level is 10%, and then it is left tail. Okay, so we check the table now. F19. Okay, so our critical value is 16, then our degree of freedom 16, then our P is 0.9, so we take 1.337. Okay, so you have to know that this is the left tail, negative 1.337. Okay, now our test statistic is negative 0.688, which is here. So we do not. Okay, we say negative 0.688 is greater than negative 1.337. Do not reject HO. So conclusion, mu x minus mu y equal to 0. Okay, so we just stop here first. Anything we continue again in our next lesson.